For decades, conservation relied on a strategy of strict containment. We drew hard borders around pockets of nature, creating walled-off reserves designed to keep the wild inside and the modern human world out. But treating living ecosystems like static museum pieces has a fatal flaw. Ecological strategists are now watching these isolated havens fail. When we fence a habitat into disconnected fragments, the internal system cannot sustain itself. It triggers a slow-motion ecological collapse. The immediate consequence falls on the wildlife inside. Animals become physically trapped behind these boundaries. Once confined, a population loses two critical survival mechanisms: the physical space required to migrate in response to environmental stress, and the genetic diversity provided by new breeding partners. The traditional model of protecting isolated spots on a map actively accelerates widespread functional extinction by starving ecosystems of the space they need to breathe. This failure has prompted a change in terminology within modern environmental policy, the active retirement of the word conservation. The reasoning is purely mathematical. In many industrialized nations, there is simply so little pristine nature left that merely protecting the remnants guarantees long-term systemic collapse. The replacement framework is recovery. This requires moving away from guarding a fragmented fortress and instead reconstructing an ecological infrastructure from scratch across the entire landscape. Old policies prioritized scenic preservation. The new approach, known as network thinking, treats the landscape as an active web of functional processes. These processes include trophic cascades. A trophic cascade is a chain reaction where one change, such as the introduction of an apex predator, triggers significant effects throughout the entire food web, even improving the health of the soil. If a reserve is physically beautiful but lacks the pathways to bring in outside pollinators or those roaming apex predators, the internal food web eventually unravels. Reversing functional extinction requires abandoning the illusion of untouched nature. Planners must actively engineer and rebuild nature's infrastructure across vast distances. Landscape connectivity is a strict biological imperative. It is the only physical mechanism capable of mitigating two distinct existential threats to isolated populations. The first threat is inbreeding depression. This occurs when small, isolated groups mate with close relatives, gradually losing the genetic resilience required to fight off new diseases. Networks solve this by facilitating continuous gene flow between separate groups, effectively keeping a population's genetic software updated and robust. This diagram illustrates the second threat, a shifting climate envelope. As global temperatures rise, the specific temperature and moisture zones a species requires to survive migrates northward or to higher elevations. If a species is trapped behind a geographical or man-made fence in a warming world, its survival zone moves away, leaving the habitat lethal. Connectivity provides the physical highways necessary for these species to track their shifting climate envelope and migrate toward newly suitable environments. Without these corridors, we witness the functional extinction of entire biological lineages that literally have nowhere to run. The structural architecture required to build this connectivity across a highly fragmented landscape relies heavily on the Lawton principles. This map lays out the transition. It starts with the first structural component, core areas, which illuminate here as large green hubs. These are high-quality environments, often existing protected reserves, where wildlife currently thrives. They act as the foundational engines, building strong, stable source populations. The second component connects them. These are corridors and stepping stones, forming the physical links between the isolated cores. They function as the highways of the natural world. A corridor might be a continuous linear strip, like a dense hedgerow, while stepping stones are small, distinct patches, like farm ponds, that allow species to navigate hostile terrain. The final component is the permeable matrix and its surrounding buffer zones. This represents the vast landscape of human infrastructure between the reserves. Making this matrix permeable involves managing surrounding farms and suburbs using environmental land management, or ELM, schemes. ELM schemes are UK programs that pay farmers and land managers for environmental services, like habitat restoration. The Lawton Blueprint redefines the human role. People are no longer viewed as intruders to be walled off, but as active managers and participants in a shared living landscape. Linking habitats is not universally beneficial. It carries immense strategic risks. This introduces the connectivity paradox. The very physical links designed to save populations can actually destroy them if not managed with absolute precision. We can see this in the conduit effect. Corridors can inadvertently act as an expressway for invasive species and lethal pathogens. A highly connected landscape allows threats like avian flu or ash dieback, a fungal disease killing millions of trees, to sweep through a region with devastating speed, bypassing natural geographical barriers. The second major risk is the sink effect. This happens when a poorly planned corridor funnels animals out of a secure core zone and directly into a high-risk area, such as a green strip terminating at a high-speed motorway. Connecting two woods on a map carries a severe engineering risk. Executed poorly, it acts as an ecological death trap for the very species it was meant to save. Planners must differentiate between structural connectivity, which simply means two areas are physically touching, and functional connectivity, which measures whether the target species will actually cross the gap. Consider the scale of human infrastructure from the perspective of a small beetle. In the beetle's reality, a two-lane paved road is an impassable wall. For a migrating bird, that exact same road is entirely irrelevant. The success of trophic cascades and gene flow relies entirely on this functional, species-specific movement, not on human assumptions about what looks connected from the sky. Designers must architect the landscape for the physical, ground-level reality of the animal, ignoring the aesthetic symmetry of a map. This biological theory is now transitioning into legal reality. In the UK, a nationwide rollout of these functional networks is legally mandated by 2026. The engine driving this is Biodiversity Net Gain, or BNG. BNG is a planning requirement where new developments must increase the total biodiversity of a site by at least 10%. To direct this effort, regions are divided by local nature recovery strategies, utilizing specific opportunity maps to dictate exactly where ecological investment will yield the highest functional return. Developers trade biodiversity units in a private market. Destruction at an urban site generates monetary flow into a nature restoration fund. This causes nature displacement. Developers pay the fund instead of fixing nature on site, trading urban nature for recovery in remote, inaccessible rural areas. While this market mechanism may successfully achieve landscape-scale goals on a spreadsheet, it risks breaking the social contract of conservation by trading local ecological access for distant gains. As this market-driven model approaches its full 2026 rollout, it faces one supreme existential risk: the creation of paper networks. Legally mandated corridors and offset zones do not become functional habitats overnight. They require a strict minimum 30-year maintenance period to mature into living ecosystems. But this biological requirement clashes with economic reality. Local councils are chronically underfunded, lacking the physical boots on the ground required to actually police these long-term developer commitments. This forces us to question the fundamental premise of the entire system. Can a purely market-driven approach, centered on trading 10% metrics and digital units, truly restore the complex biological interactions of wild places? Or are we simply commodifying the living landscape, reducing ecological function to a tradable asset just to satisfy corporate balance sheets? The true success of biodiversity networks will not be measured by the digital lines we draw or the units we trade today. It will only be proven by a rigorous, decades-long commitment to sustaining functional living landscapes.